Okay, let's start. I will talk about some ideas that between technical mechanics and relativistic equations, the so-called screw algebra and Grassmann manifolds and all that. I think my talk will be very simple and understandable by everyone. Here is outline of my talk. Recollecting the third Newton's law, it is well to remark that forces emerging from an interaction of 2 point-like bodies act along a common straight line. This means that force is characterized by line of action. That is, force is a sliding vector rather than a free vector. And in contrast to relativistic dynamics, where force is a bound vector, in relativistic dynamics, force is bound vector in order to observe ball rigidity condition. In classical mechanics, force has no point of application. I should tell something. Sorry, I should tell something about difference between free bound and sliding vectors. A bound vector is a directed line segment with a fixed initial point. A free initial point of a free vector is not fixed and can move throughout whole space. And initial point of a sliding vector can move only along the line of action of the vector. I show more precise definitions. The problems that from which I want to begin is the problem of addition of two forces that act on a rigid body. We consider first two-dimensional case. That is, the problem is how to add forces so that the moment of the resulting force equals the sum of the momentum. In order to solve this problem, we have to consider forces as sliding vectors rather than free or fixed vectors. Since we consider sliding vectors, it is natural to find the point of intersection of lines of actions and then move each vector to the initial point and use the parallelogram rule. Thus, we obtain the resultant force, which is also a sliding vector. When the forces are parallel, there is no intersection point. And in order to add these forces, we should divide the line segment that connect the initial points of the forces F1 and F2, and to use the ratio between the magnitudes of these forces and divide this segment according to this ratio. Then we find the resultant force, which is also a sliding vector. This is a rule for addition of parallel sliding vectors. When forces are directed in opposite directions, their sum is also a sliding vector. However, if the magnitudes of these forces come close to each other, this sliding vector moves to infinity. However, sum of antiparallel forces is also a force, and in this case, the momentum of these forces equals to the momentum of the resultant force about any point in this plane. And the most interesting case when the forces are equal to each other in magnitude and directed oppositely to each other. Thus we come to the concept of force couple or torque. It is pure torque, which can be considered as a free vector orthogonal to the plane under consideration. And the sum of two forces is not a force. It is an exceptional case. This is more interesting in three-dimensional case. In three-dimensional case, the problem of adding forces acting along skew lines is more difficult. I will consider this problem in more detail. I remember that the moment of resultant force should be equal to the sum of momenta of these forces. Firstly, we add these forces as free vectors, choose a plane orthogonal to the resultant force, and move initial points of the two forces under consideration to this plane. Then we decompose each of the forces under study into orthogonal and parallel components to this plane, and only then we add parallel components and orthogonal components as sliding vectors according to the rules considered above. The resultant picture is as follows. We add two orthogonal components as free vectors and obtain the resultant force, and thus we fix the line of its action. And in the plane orthogonal to the resultant force, we add a couple of force, the force couple. Thus we arrive at the situation with a general in three-dimensional case. The sum of forces is not a force. It is a force and a force and force couple in the orthogonal plane. Such a combination, force and force couple, or pure torque in the orthogonal plane, is called a screw. Thus, sum of the forces is a screw rather than a vector. Thus, we come to the problem how to add screws. The first idea is to place the screws on intersecting lines. However, when screw axes are skew lines, this problem is more difficult. And we come to the problem how to locate a screw in some point beyond the line, or beyond the line of its section, or beyond the axis of the screw. When we place, when the axis of screws are intersect, then the problem of adding forces or adding screws is simple, and the solution is written here. We simply add the free vectors and sliding vectors that form each of the screws, and this trivial. That if we have a screw that is a pair of sliding vector and free vector in some point, how can we transport this screw to another point? The rule that solves this problem is written here. We should consider a pair of non-parallel vectors. That is, sliding vector is becomes not parallel to the free vectors, and the momentum in the point beyond the screw axis is not parallel to the force. Thus, we can transport a screw to any point in the space. And the inverse operation, that is, finding the axis of a screw, given we have a pair of vectors of force and momentum, can also be solved by the same formula. We change. The answer of for finding the axis of screw is written here. And thus we have the procedure of transportation of a screw to any point and finding the axis of a screw given a pair of sliding and free vectors. Performing this procedure, we arrive at the algorithm of adding of two screws. First, we fix initial points of the two screws, transport one screw to the initial point of another, find their thumb, find the main axis of the resultant screw, and transport the obtained vector pair to its main axis. Clifford suggested to use complex number for screws algebra. However, instead of imaginary unit, he suggested to use the parameter whose square equals 0. For this reason, I will call this number complex instead of complex. The algebra of this number is rather simple. We can define trigonometric functions for this numbers, and we can use expression for screws using this nilpotent parameter. We can introduce the concept of unit screw, which is given by the pair where vector of momentum is 0 and vector of force is unit. We can consider, we can express arbitrary screw in terms of unit screw in the same direction, and we can find absolute value of a screw, which is given by a complex number. And we can define scalar product of two screws, and therefore we can define the cosine of an angle between skew lines as a scalar product of unit screws along these lines. We can consider cross product projections of a screw on an axis, mixed products, linear transformations, functions of screws, and so on. These complex numbers make it possible to perform all these operations. Angular velocity is analogous to a force. It is also a sliding vector. And addition of angular velocity is similar to addition of forces. In particular, if a couple of force gives pure torque, a couple of angular velocities gives pure velocity. And there is a similarity between dynamical screw, that is wrench in English literature, and kinematical screw, that is twist in English literature, where force is similar to, is an analog of angular velocity, and moment is analog of velocity. Screw algebra is helpful in machinery. In particular, this system of revolute prismatic joints, where each joint is free to move along axis and free to rotate along them, can be solved by using screw algebra. We can introduce complex angles of rotation at each point, and the resulting screw of rotation is given by this formula. And each link between joints can also be characterized by the complex number. Thus, this very complicated problem, very tedious problem, can be solved in a few algebraic manipulations. Here, I would like to show a list of literature on this subject. It is mainly technical literature, literature in engineering, in editions for engineers. However, there are also more or less fundamental investigations. It is. I would like to mention the authors who elaborated in the subject, and authors of screw calculus in Russia are Pyotr Ivanovich Kotelnikov, who worked in Kharkov and Kazan University. I didn't find his photo, and his son Alexander Petrovich Kotelnikov, who is one of the authors of screw theory. His son is well-known radio engineer in the Soviet Union. It is dynasty of Kotelnikovs. And other people who work on the subject is Louis Poinsot, William Clifford, Robert Ball, the author of a monography on screw calculus, Michel Schall, and also Julius Plucker and Hermann Grassmann. Something should be said about relativistic generalization of screws. There is no works on the subject, however, it may be of interest, because an elementary particle is characterized by helicity and momentum, and analogous quantities characterize velocity of rigid body, sum of forces acting on a rigid body. And however, there is a difference between rigid body dynamics and the relativistic case, where force is a fixed vector rather than a sliding vector, because one needs to observe Born rigidity in relativistic dynamics. And uniform motion of a relativistic rigid body can be described by kinematical screw, as in the case of classical mechanics. However, angular velocity of relativistic body cannot be changed without interaction and without breaking Born rigidity conditions. It is in this sense a relativistic body, classical relativistic body, similar to elementary particles whose helicity cannot be changed without interactions and breaking the state of breaking the state described by representation of Poincare group. Yet another approach to sliding vector is as follows. We can characterize sliding vector F by its direction and its moment with respect to the origin. And we can consider a free vector associated with the respective sliding vector, and the couple of free vectors also characterized the force as a sliding vector. And these vectors should be orthogonal to each other. We can embed our three-dimensional space shown in rows here into four-dimensional space and consider forces as a b-vector in this four-dimensional, as b-vectors in this four-dimensional space. An exceptional case is pure torque. Pure torque in this picture can be described by the plane t equals 0, and it cannot be projected on the plane t equals 1. This picture motivates have motivated Julius Plucker to introduce coordinates for describing vector of force. The Fluker coordinates of the force are more general. They characterize these B vectors. Vector of force is characterized by these three determinants, and vector of momentum is characterized by these three determinants. Fluker discovered that only some of antisymmetric tensors can be expressed in terms of B vectors. More precisely, only those tensors that satisfy Fluker's condition can be represented as B vectors. In our case, Fluker's condition can be relates to the orthogonality condition between force and its momentum. In the general case, an antisymmetric tensor in four-dimensional case can be represented as a sum of two B vectors. In our case, the former B vector is related to force, and the latter B vector can be related to pure torque. And as I explained previously, this representation is not unique, but it always exists. And the two planes determined by such B vectors has been studied by Grassmann, and Grassmann generalized this construction to the case of an arbitrary dimension. It is important that forces and torques can be considered here on equal foot. A similar construction was used by Roger Penrose in order to describe the manifold of light rays in Minkowski space. An arbitrary light ray can be characterized by a light-like vector and by its moment about origin. As I explained previously, the moment is described by a B vector. Penrose noticed that this B vector can be represented in terms of spinors, and the second and his second observation is that vector m pointing to the light ray can be chosen as light-like vectors. It is shown here. If we choose arbitrary vector indicating the light ray, we can choose a light-like vector that will point to the same light ray. This couple of light-like vectors can be expressed in terms of two spinors, provided that the spinors are related by the formula, where m prime is the momentum is the light-like vector indicating the light ray. This pair of spinors represents the light ray, provided that the product of the corresponding spinors is purely imaginary. Such spinor pairs is called a twistor, and the relation between two spinors can be considered also from another side. That is, the incidence relation maps a point in Minkowski space into two plane in twistor space. Thus, we have a description of Minkowski space as a Grassmann manifold in the twistor space. Look, I should say the following, that representations of Poincare group have an interesting analog in the rigid body dynamics. And the ideas of Grassmann manifolds on odd numbers, complex calculus, and the like are tightly connected with industry and engineering. And mathematical formalisms of screws proved to be fruitful in vast areas from engineering to relativistic body dynamics.
Thank you. Thank you for understandable and surprising talk. Are there any technical questions? The speaker? Yeah.
Could I ask?
Sure.
Could you show?
No, you better come here, otherwise nobody will.
In the middle of your talk, you showed some page from probably old textbook. This one. Where is the source of this page? Probably it's a copy of old book textbook or not.
The author of
No. I mean, who is author of this book? Because it's page 199.
The author of this book is Berg.
Okay. And
He cites himself.
But there is a title of this book.
Screw calculus, screw theory of screws.
Okay. Okay, thank you.